Hi, class. So what we want to look at now are the actual reactions of alkenes. And so we've seen a few reactions so far, but this is the first time we're truly going to see an in-depth look at an array of reactions with a functional group. And so before I get into the specifics of alkene reactions, one of the things I wanted to highlight is, as you move forward, when you're looking at reactions for a molecule, what you want to find is what functional group are you reacting, right? So if you've done alkanes, right, you can know that, okay, here's an alkane. What reaction does it do? Now, as we add functional groups, that's where your attention should go. And hopefully that's what the zigzag form is doing, is highlighting that functional group that you want to focus on. All right, so what we're going to do in this chapter is we're going to look for the double bonds, and we're literally going to add across those carbon bonds. Right? And remember, it's that pi bond that we're going to break. Right? So we're still going to keep that single bond, so we're not cutting the molecule, at least right now. There's one or two reactions to do, but for the most part, what we're going to do is break that pi bond and add to each one of these carbons. Right? So depending on what these groups are, you're going to add one of them to the inside carbon and one of them to the outside carbon. Right? And we lose the double bond. Okay? So for the most part, this is going to be our theme. All right, so when you see a double bond, we know we're going to add across that double bond. We're going to lose the double bond and keep just a single one. And each of the two atoms are going to add to the two carbons that were part of the double. All right, so one carbon on the outside of the double bond, one on the inside. Each of them will get one of the atoms and we lose the double bond. All right, so this is generally the theme that we're going to do over the next handful of reactions. A couple terms as we're kind of looking at this and trying to figure out how is a good way to predict what we're going to do or what's going to happen. All right, so a nucleophile is a source of electrons, right, and typically has some negative character. The easiest way to see this is one of two ways. Is if it has a negative charge, right, then it's obviously got some negative character. The other thing you should think about is some kind of lone pairs. All right, so typically it's got to have some lone pairs, right? And the other one that we'll see today, right, is our double bond. That pi bond can be our source of electrons, right? So that negative character. So it's got to be that source of electron density, right? And what you want to think about is those electrons are going to reach out and grab that electrophile. And so typically the way we write nucleophile is Nu, and it usually has some lone pairs, a negative charge. And then we can have our electrophile. And the one thing when we're drawing arrows is our nucleophile is going to typically reach out and grab that electrophile. Let me show you one. So if we had something like sodium hydroxide, right, so there'd be a sodium, OH, and then HCl. The reason I put a little space in between the sodium and the oxygen is, remember, this is an ionic bond. So the sodium would have a positive, oxygen would have a negative. Over here, this is a polar covalent bond. And if you remember from before, our electrons are going to pull towards the more electronegative atom. Okay? So my chlorine is going to have a negative charge. Hydrogen is going to have a positive. All right, so what you want to think about here is that they're going to behave like magnets, right? So the opposite charge always attracts, right? So if you ever took two magnets, you try to put them together. If it's the opposite charge, they stick together really nicely. If they're the same charge, they're going to repel. Same thing is going to happen here. So my negative charge is going to reach out and grab my positive charge. Right? And so that blue arrow with those electrons reaching out and grabbing that hydrogen are going to pull that hydrogen off. And then typically there's a second arrow that shows we're leaving that chlorine behind. Okay? And we're going to tie all these together, but now let's look at some different examples. So now let's look at this one. So I think at the very, very beginning, I told you we want to focus on the double bond. And so actually, let me highlight it in green so we know that's where our attention should be. So it's going to be these two carbons, right, and the double bond. And we're going to add HBr to it. Right? So our source of electrons would be that double bond, right? And so that's going to be my nucleophile. So let me just write that. So for this one, my nucleophile is going to be that double bond. And that double bond is going to reach out and grab that hydrogen and kick off the bromine, right? Because remember, the hydrogen has a slightly positive charge, just like we saw in the chlorine on the previous example. Now, what makes this one a little bit tougher is you could add a hydrogen to the carbon on the outside or the inside, and then you could add the bromine either to the carbon on the inside or the outside. So you could add to either one. Now, they only add to one of them, and so we want to be able to predict which way it's going to go. And this idea of having a selectivity for one carbon versus the other is called regioselectivity. Right? So the term regioselectivity just means that when you're adding across a group of atoms, that one product is formed over the others, right? That there's a bigger preference. And so we see that here in terms that this molecule is the one that's formed, right? And so in theory, it looks like we should be able to form both, but we only find that one in the blue box, right? And the reason for that is, and we'll go through the mechanism, it has to do with the intermediate with a carbocation, but it's going to follow Markovnikov's rule. So Markovnikov's rule tells you that if you're adding a group with a hydrogen and a halogen, or the same thing with water, we're going to add the hydrogen to the carbon with the most hydrogens. All right. So you're going to add the hydrogen to the carbon already having the most number of hydrogens. All right, so what does that mean? If we look at these two, this carbon has 2 hydrogens, and so the one already with the most number of hydrogens gets the hydrogen. Right? And by default, the bromine goes on the other. Right? So you're always going to add the hydrogen to the carbon that already has the most hydrogens of the double bond, right? We're only comparing the two in green, and then the halogen goes to the other carbon. So let's look at another example. So now I put in the zigzag form, so it makes it a little bit tougher because we have to think about the number of hydrogens on each carbon. So our choices are these 2 carbons in orange. If you look at the bottom one, right, remember every carbon is going to have 4 groups. So it's 1, 2, 3, and then that double bond counts as 4. So there actually isn't any hydrogens on here. And so let me just put 0 hydrogens. On this one, it's got 3 bonds, 1, 2, 3. So there's 1 hydrogen implied. So if we were doing the same reaction with HBr, that's telling me that we would add the bromine to that more substituted one, right? And remember, the more substituted carbon just means the carbon that's attached to more carbons, right? So if we were doing substitution, we would just count the number of carbons bound to it, right? This one has 3, this one has 2. And so that more substituted carbon is going to have less hydrogens because it's attached to more carbons, right? So it's kind of the opposite way of thinking about it. So we're going to add the bromine here, and let me put it in red. So the bromine is going to go to this carbon, and the hydrogen is going to go to this carbon. And it's a horrible B. There we go. All right, so let's draw that together. The line, and my bromine, and then my hydrogen out there. Okay. All right, let's try one more. So I'm going to switch it up and put a ring. So a cyclo group. This time we'll do it with HCl. All right, so go ahead and pause the video, draw the major product, and then we'll do it together. All right, let's see how everyone did. So the same as before, you want to compare these 2 carbons, so the one on the left and right of the double bond. And we want to see how many hydrogens are implied. This carbon already has 4 groups, right, because we count the double bond. So there's no hydrogens on this carbon. On the one on the right, there's 3 bonds to it. So there's going to be 1 hydrogen implied. And so whichever has the most hydrogens gets the hydrogen from our HCl. So since this one has 0 and this one has 1, we're going to add a second hydrogen, the one here, to this molecule. So So let's go ahead and draw it. And remember, we lose the double bond. So if we redraw our molecule, we keep the methyl group on top. My chlorine comes off here. And we add a hydrogen. And so just to kind of color code them, let's do this. Let me keep this one in green since I did green over there. So one of those would have been the hydrogen that's already there. And then the other one would have been the hydrogen. Oh, sorry about that. Would have been the hydrogen that came from the HCl. All right. So same idea, it doesn't matter if it's HCl, HBr, HF, HI, exact same reactions. Right? And we're going to talk about doing the same thing with water. All right, so now let's actually look at the arrows. So one of the things I could ask you for is the mechanism. And the mechanism is a step-by-step detailed explanation of how the product is formed, right? And so this is going to give us some insight into exactly what's happening, right? And this is going to help us predict other reactions. All right, and so what we want to do is look at the double bond. And remember, this is going to be my nucleophile. So the double bond is going to reach out and grab that hydrogen. Right? So it's going to grab the hydrogen and push the electrons onto the bromine. All right, these on top, these partial charges, won't typically be drawn out for you. It's something up to you to come up with, right? And remember, and let me show you where those came from. If you have HBr, the bromine is more electronegative, right? So it's going to steal the electrons. So that arrow shows me which way the electrons go. We think of electrons as having a negative charge. So that's why the bromine builds up a negative charge and the hydrogen builds up a positive. Right? And so the nucleophile, the electrons are negatively charged. So it's going to try to find something that has a positive charge. So that's why those electrons are going to grab that hydrogen and then kick off the bromine. Right? The bromine has 6 electrons shown, and then those 2 electrons from the bond go onto it. And so that's why bromine has 8 electrons over here in a negative charge. I added that hydrogen, and we get a carbocation on the other one. And the carbocation comes from the fact that this had 4 bonds, right? This hydrogen would have been coming off of it. So it had 1, 2, and then 3, 4. So it had its octet rule. Now, if you go back to how we could figure out our formal charge using the valence electrons minus lines plus dots, you'd actually see if you only have 6 electrons, which carbon does now, right? So it has a second bond to the hydrogen and a third bond to the carbon. So it only has 6 electrons. So that's why it has a positive charge. All right, so that's my carbocation. Same idea in step 2. We want to take these charges and match them up. So we're going to push the electrons into the carbocation, and that's where we add the bromine. Right? So it's always a negative charge is going to push into a positive, right? So we're going to feed into that carbocation, and that's why the bromine adds.